So yeah, I'm going to talk today about some work we've been doing mostly on multi-fingered manipulation, but also some stuff on multi-object manipulation. And I'll briefly talk about tactile sensing and vision, so we can say it's multi-sensory. So, it's like a multi talk if you want. So at a high level, I'm, fundamentally interested in autonomous manipulation. I want to answer questions of how can robots fluently manipulate objects with which they've never encountered before, right? So how can we do this? So in the past, I've come at this problem in a number of ways. So one is, how do we understand the world interactively? So we can have robots learn to segment and detect objects by pushing them. We can also build object models through touch to have 3D understanding of the world. More recently, we're looking at how can we simultaneously build these 3D models while doing goal-directed behaviors, like picking an object up and putting it in a new location. And also, how can we learn not just about the 3D shape, but things like the mass, center of mass, and inertia of objects through tactile sensing, again, while potentially trying to achieve some task at the same time. Another line of work I've done a decent amount of work in that I'm not going to be talking about in detail today is how we can perform robust feedback control with haptic and tactile sensing. And particularly here again, we're focusing on objects and environments with which we don't have models a priori. And so to perform these tasks, we often leverage learning for the robot to generalize its predictions of what will happen from previous encounters with other objects to these novel objects. And we've shown how we can do things like learn accurate force prediction from these tactile sensors so that we can delicately place objects, we can detect slip, and we can perform hybrid haptic position control on varying surfaces like sandpaper. Okay. But today, I'm going to mostly focus on multi-fingered manipulation. And when we talk about manipulation, the first thing we often think about is grasping. And so the natural question arises of why do we want multi-fingered grasping as opposed to just using parallel jaw grippers, which are more standard in robotics. And this figure from the Encyclopedia Britannica, I think, really highlights the benefits of multi-fingered grasping. So first, if you imagine picking up something long and heavy, like this spear, if you were to do that with a parallel jaw gripper, right, there's a large moment that's being put, and it's actually quite hard to provide the stability necessary for carrying this large object. So that's one thing we get, increased stability. But at the same time, if we want a robot that can pick up heavy stuff, but also maybe perform tool use so that it can help you fix things around the house, right? We want dexterity in the hand. And so on the right, you see this hand holding this stone for some plaking task, right, which requires delicate force manipulation to accurately perform it. And so we also get versatility and dexterity through these multi-fingered hands. And as some examples of that, what we really care about doing is not just grasping objects, but doing things with them after we've picked them up. And this is what motivates kind of the second part of the talk, which is going to be on in-hand manipulation. So if we want to perform tool use things like using a jeweler's screwdriver on a robot so that it can, open up these devices and repair them without having to have specially defined end effectors for each tool, or also just doing things like grasping in clutter to use an object, right? So for this mustard bottle, you can't really get the side grasp you want without having to either move objects around or, knock them over potentially. But the grasp that you do have available to you where you're performing this overhead grasp, if you were to then squeeze the mustard bottle, right, the robot would cover itself in mustard, which we don't want. So, right, we need some way of moving from this overhead grasp to this side grasp so that we can perform the task we care about. This in-hand manipulation tasks are in themselves interesting, but they also motivate a need for a variety of grasp available to an object, right? So when I talk about grasping, I'm going to talk a little bit about not just picking up the object, but providing specific constraints or having the grasp have specific qualities that we might care about, right? Like picking it up with the fingertips as opposed to enveloping the grasp with the object with a power grasp. So the outline of the remainder of my talk is going to look like this. So I'm going to first talk about multi-fingered grasp planning as probabilistic inference. This is cover a number of papers we've written over the past years on this topic. I'll then talk briefly about some trajectory optimization work we've done for in-hand manipulation before moving on to this multi-object manipulation using graph neural networks that Dimitri mentioned at the beginning. Okay. So we can very, broadly define, separate grasping approaches into two camps, right? Kind of model-based approaches where you assume you have a 3D model of the object, potentially also dynamic information, and sensor-driven methods where you're just given, an image or a point cloud of the object that you're trying to manipulate, where typically we leverage things like learning in order to generalize to these new cases. We're very interested in this learning-based approach because it allows us to, trivially deal with new objects in the same way we would with previously encountered objects. And I'm gonna focus on that today. Okay. So a kind of standard pipeline for learning-based grasp classification will look something like this. So we have some sensory input, which I'll call Z. So for our cases, it's gonna be, a point cloud or an image patch coming from a connect. So we'll always have some 3D information of this partial view of the object. And then we additionally have some representation of the grasp. For parallel jaw gripping tasks, this is typically just like a bounding box or a 3D reference frame in the frame of the object. But for multi-fingered hands where we have more degrees of freedom, we have to have a richer representation. And so for ours, we have a 3D reference frame of where the wrist should go. And then additionally what we call the grasp pre-shape. So this is the first 2 joint angles of each of these fingers. So the hand has 16 degrees of freedom. So 4 degrees of freedom per fingers. So you can think of the first 2 joint angles kind of say where the fingers are pointing. And then after we move there, we have a controller that's just gonna close the hand. Okay. But we're gonna learn to predict whether this pre-shape before we close it is successful or not. So if we have these 2 inputs, we can then pass them through some classifier, which is parameterized by some parameters W that we're gonna learn. And we predict a binary variable Y of whether we're gonna be successful or not in grasping the object. Okay? And in our case, we're also gonna have an associated confidence in that prediction, right? So it's not just, is it gonna be successful or not, or what do we think the probability of being successful is? Okay. So given one of these learned models, the question arises of how do we actually synthesize a grasp, right? How do we do planning now that we've done this learning? And there's a few approaches that have been proposed in the past. So by far, the most dominant approach is to simply sample, right? I generate a large number of potential grasps, I evaluate them with my classifier, and I pick, say, the one that has the highest confidence, or in some cases, maybe I learn a score of better grasps, and I select that. Okay. The problem with this is they generally rely on some heuristic to generate the sampling because the space is far too large to efficiently sample exhaustively. And this becomes even way more harder when you move to many degree of freedom hands, like these multi-fingered hands, right? And so what's typically done there is you actually, instead of, you maybe use some external planner to propose some grasps and then evaluate them. There's an additional problem when you use these external planners is that you're adding some bias from those planners into the method. And we'd really like to remove the reliance on some external planner and have the learner be its own source of generating the grasps. Okay. An alternative formulation is instead of doing grasp classification, we can do regression, right? So instead of giving those grasp parameters as input, I just make them the output of some neural network, say, and I take the image and I directly predict, oh, these are the joint angles you should have. There's a few problems with that. So first of all, it can't learn from failed grasps. Okay? And for example, there's a data set that we recently created for grasp learning had something like 5,000 grasp attempts, and maybe 1,000 of those are successful grasps, right? So the majority of times when we try to grasp something, it's gonna fail if we don't have a lot of knowledge put in a priori. And so this makes these regression methods data inefficient. They're much harder to learn exhaustively. Additionally, they're implicitly assuming that there's kind of one best grasp per object, right? If you're only outputting a single grasp as the output of your regression, you're going to assume that it's the best one, and that's kind of a problem because we know both from human subject studies as well as robotics that depending on the context and the task you're trying to perform, there are different grasps that might be more suitable, right? Even though all of them maybe have similar stability qualities. So the final alternative, which you've probably seen a lot of work in because it's so popular these days, is reinforcement learning. Reinforcement learning is cool. I do work in reinforcement learning, but I think there's two fundamental issues here for grasp learning. So first, it's data inefficient as well. You have to generate tons of real robot trials to learn how to grasp effectively. And additionally, I think a lot of that is wasted time in that you're learning to do things we already know how to do well in robotics, right? I know how to reach out to an object with a motion planner or even a simple straight line controller. Why do I need to learn all of that before I can just learn how to pick it up? So we'd really like to focus our learning efforts on the hard part, which is what is a good grasp, because we don't know how to do that. Okay. So given that, I'm going to tell you now an alternative that we've proposed for doing grasp planning with these classifiers. So if we look at a classifier, the important thing that we need to have for our approach is that it's, or two things. So one, that we have this probabilistic output, like I said. And two, that the function of the classifier is differentiable, which motivates partly the use of neural networks for these applications. And then we'd like to solve the following map inference problem of finding the grasp parameters theta that maximize the probability of success given the learned parameter weights W and the sensory input Z. Right? And so if our classifier just directly predicts this likelihood, then we can just say this likelihood is equal to, the classifier F. To solve this optimization, we'd also like to impose certain constraints on it. So for example, we can't move to arbitrary joint configurations of our robot. We have joint limits. So we can add these bound constraints over our decision variables of the joint, of the grasp preshape while doing the optimization. Then because our neural network is differentiable, right, but it could be some other classifier that's differentiable, so a Gaussian process, for example, we can just do gradient-based optimization over these parameters. So I give some initial theta, I do a forward pass through the classifier to predict the probability of success, and then I can use, say, backpropagation to efficiently compute the derivatives of this function with respect to the input, and I can iteratively perform this until I converge to some local optimal. Okay. So does this work? So we created a large training set in simulation using the same paradigm, and then we're going to test it on the real robot. I'm going to show you results for this robot. So this is our 7 degree of freedom KUKA arm with this 16 degree of freedom Allegro hand. Importantly, this approach also works for parallel jaw grasping. So we did additional experiments on the Baxter, which I'm not going to show, but I'm putting it here just to say that while we're motivated by multi-fingered hands, in no way is this restricted to multi-fingered hands. So how do we do? So first, let me tell you what I'm going to show. So here we have the success rate. So this is of the total number of attempts we tried for grasping, what number were successful. Where successful means the robot could pick up the object 15 centimeters and hold it there for a few seconds without it dropping. We're testing on several different objects, which are shown by name here. So we also we have a couple comparisons. So the first comparison is a simple geometric heuristic, which says finding a 3D bounding box for the object, align the palm with that bounding box, and close the hand. Right, that has really, so there's 6 possible grasps. You can't do the one on the table, right? So it's more like 5, and we're going to restrict that to 3 because we're not going to try to reach around the back of the object. Okay. So here's how that does. So let's just think of this as a baseline. So that simple method, is working in its best, for the best object only, less than 50% of the time. We can evaluate if the learner is doing anything good by, instead of just trying all of those 3 grasps, evaluating each one with the neural network and saying, this one we think is going to be most successful, which we call max evaluation. And that improves in general, right? So what this is saying is the learner is learning something. It is helping improve the grasp performance. But we haven't added our inference, right? So this is, you can think of an informed sampling approach. If, however, we initialize with these heuristics and then run the optimization, success rates increase dramatically, right? For some objects, we don't do any better, but for an object like this large picture, we go from having around 20% success with the other alternatives to 100% success across the 5 trials in these experiments. Okay. So, think of this as the first bit of work that says, doing inference is good, right? It does give you better grasps than just an informed sampler. We also tried exhaustive sampling, like generating 100 samples and trying the best one. And it worked so poorly that we didn't even try it on the real robot. We train in simulation on a bunch of objects, like 100 or so. So that's really what's going to limit us in terms of how we can generalize. None of these objects were seen in simulation except for the Pringles can, which is one of the more simple objects. I will note that the can in simulation was a different flavor than the can in the real world. So yeah. So the input here is an RGBD patch, so that color information is there. But I'm going to show you some more results from later work where we throw away color and we just use the depth information. Okay. So here's qualitatively some examples of what these grasps look like. One thing you might note is these aren't the prettiest grasps. The fingers are kind of squeezing around each other. They leave something to be desired. Okay. Right, so the main point right now I want you to take away, right, is that we'd like to leverage, using this planning as inference, we can leverage deep neural networks to get really rich representations of the world and use state-of-the-art learning techniques to predict success. But we can outperform previously proposed approaches to planning with these deep neural networks, while also being more data efficient. And something that I didn't really talk much about, but is going to motivate some of the stuff I show in a minute, is we can embed other model-based knowledge into this grasp optimization, right? So the part I did talk about that a little bit is the joint constraints, right? That's a very simple model, but it's a model nonetheless. And by thinking of this constrained optimization, it gives us a language where we can, have a common language between learning and model-based approaches. And so I'm going to show you at least one more example of adding more complicated constraints in the forms of models in a minute. Okay. But first, I'm going to talk. This is actually you could think of this as another case of that. So I showed you those grasps before. They weren't very pretty. Additionally, they were all what we would call power grasps, right? So there's high amount of palmar contact between the hand and the object. And they weren't, say, picking it up with the fingertips. And like I showed you at the beginning, I want to do in-hand manipulation with these objects. And if I want to have dexterous, manipulation of the objects, I need to pick it up with the fingertips, which we would call precision grasps. And so we'd like to look at how can we do this with our approach. And also looking at the literature, even most planners, but learning-based methods as well, either give you precision grasp or power grasp. There's only like one method we had found that claims to do both. And so this is like a more generic problem for grasping. Okay. So here's the same setup we had before. How can we add grasp type? And we've changed our optimization now, where we add this extra variable g, which is going to be some discrete variable that selects between grasp types. Right? And for this talk, I'm only going to talk about 2, precision and power. But we could have an arbitrary number n, and this will still work. And so how do we add this? Well, we just learn another classifier. And we're going to separate the data to say some data are precision grasp and some are power grasps. And we can still use the same approach. We can either specify I want a precision grasp and set G to a specific value, or you can simply say I want the best grasp possible and optimize over all values of G as well, which in this case is just you run 2 optimizations in parallel, right? One for grasp type 0, one for grasp type 1. So another thing we do is we add a prior over the grasp parameters data that we're also going to learn. And I'm going to tell you the details of that after I show you the results because it deserves its own explanation. Okay. But so the main thing is using this grasp type optimization for the same objects given in the same pose, we can now specify precision or power and force the robot to generate such a grasp. We see that also now the power grasp we're getting look nicer. Okay? We attribute this to the fact that by separating precision grasp from power grasp, you have 2 learning problems now, but they're actually simpler learning problems in the sense that you don't have to have one learner that has the concept of all possible grasps that are successful, but instead it just needs to know, for this class of grasps, what do good grasp pre-shapes look like? So these are the qualitative results. Quantitatively, I can show you a comparison of, here's on more objects than before. So here's our heuristic for precision. Here is our previous approach where we have one unified model trying to do precision grasps. We see for most objects it does very poorly. But if we do this, precision planning with our type-based classifier, we get significant improvements. So just to complete the results here, so for power grasps, it's a similar story. It's just the overall success rates are better for everything. And for our type-based power grasp classification, we actually get 100% success across these objects we looked at. Okay? So we were lucky there, right? That rarely happens in a grasping experiment. So what this tells us is knowing about grasp types, like knowing that precision grasp exists, makes the robot better at doing power grasping. Is one way to think about the factorization of the problem we've performed. Okay. So here's some videos of the robot doing this, just to show you it really does work. After we generate the pre-shape, we get a motion plan using, I think, some form of an RRT here with some smoothing. And so here's the object in pretty much the same pose, and we're going to have the robot do a precision grasp instead of a power grasp. So we do have a slightly different controller for precision grasp and power grasp as well. Okay. You also might notice that most of the objects are pretty tall because this hand's big and clunky. So it's maybe 150% the scale of a normal human hand. Or like, not a normal human hand, like a big paw like I have, yeah. So precision grasp is one where it's primarily or solely the fingertips, and a power grasp where there's more contact between the palm and the joints of the fingers. So another thing that your question reminded me is I said at the beginning, right, we can either specify the grasp type we want, which is what all the experiments formally that we showed did, but we can also optimize over the grasp. And what we first thought was a bug, but then realized was actually the right thing to happen, is if we optimize over the grasp type, it always selected a power grasp, which means it's learned also that power grasps have a higher probability of being successful, right? Which you might interpret as it knows that they offer better stability. Okay, so I said there was another thing we added here, which is priors over the grasp configurations. And we originally were motivated for this because we thought, well, there's a number of reasons. So one is, I told you before, we had to initialize by using these heuristics. If we learn a prior over grasps, we can then sample from that prior to initialize the optimization. And we no longer rely on any external knowledge other than what's contained in the optimization and the learned models for the planning, right? So this is great. We've removed the need for an external planner. But there's also a numerical reason, and this comes to the question of epistemic uncertainty. So you can think of what I'm doing here as an approximation of explicitly modeling the epistemic uncertainty of the learned classifier. Okay. So if we look at a very simple 1D classification problem with a logistic classifier, right? We get this red curve. The cyan and pink X's are positive and negative samples, right? If I then perform my inference on this, I'm going to continue optimizing, right? I'm going to move along this asymptote until the change in the value is below whatever the numerical precision I'm using for the tolerance of my optimization. So what this means is the optimizer is just going to keep going further and further away from your training data, just to make more 9s after the 0.9 symbol, right? So this is bad, right? And the joint angles help somewhat with this, but actually in that initial work we had to artificially restrict the pose that the hand could go to not just shoot away from the object. Okay. If we learn a prior, modeled here as a Gaussian mixture model, which is what we use for this work, we learn this over all of the training data. Right? And so this really is just telling us, what's the probability that I saw this grasp shape, in my training data? You might alternatively think of it as kind of what is a weighted distance of this grasp from grasp I tried in training. Okay? And so if you think the classifier is good at predicting for grasps similar to those it saw at training, we would prefer to keep to grasp that the classifier is good at training. But by modeling it as a prior, we can model all of this as optimization over the posterior, which is the product of these two densities. Okay, so we get this nice blue curve. If we optimize it, right, we stay nice over the data. And it will drop off quickly as we move away from the data. Okay, questions about the prior kind of conceptually? So we said we want to model the uncertainty of the network. What we don't have here is any incorporation of the object we're grasping, right? So in some sense, this is nice. It's saying these are good grasps, or these are grasps I've seen, independent of object, which might make sense as a prior. But we'd like to use that information of how close is this grasp we're trying, relative to the object we're observing. So we've more recently, this paper is actually we're resubmitting today, I hope, the revised version of this. We're learning an object conditional classifier. So we also have a more complicated neural network for the classifier, which I'm not going to talk about. But in general, we have a voxelized representation of the object now. We're encoding that through some 3D convolutions. And then we're learning the parameters of the Gaussian mixture model. Right? So the means, variances, and mixing weights of a Gaussian mixture model, where we're predicting what those should be given the object we observed. So now instead of one uniform mixture model, the neural network produces one conditioned on the observed object. And for the initial work, we just used 2 mixture components. So how you pick that, is an open question, and really we'd like to learn the number over time, which is a harder problem. And we're focusing here primarily on precision grasps. So we're always using our precision controller. So this provides better performance compared to the unconditional GMM. So what might help you understand what's going on here is we can now show this neural network objects, and we can visualize what the mean of these mixture components looks like. Okay. So here are a number of objects. And here are what the mean is saying the the pre-shape should look like. So you see these are essentially kind of pointing down overhead type grasps. The other component has essentially learned side grasping to align it to the side of the object, right? This is partially biased by the training data, which is using this heuristic. So one thing we're actively working on, excuse the pun, it was not intended, is active learning, so that the robot actually generates its own grasp types to better explore the space of grasps. But this was really nice, right? We just said use two components. We didn't tell it these components are side grasp, these are ones are top grasp. It just kind of learned to disentangle them correctly. And then if we combine that with the optimization, depending on which component we sampled from, we can get side grasp or top grasp for the same objects. Okay. So the one last bit on grasping is, I said we're pre-training this on 3D reconstruction. And we pre-trained that work using a voxel-based representation. But we just found out, 3 days ago, that this paper got accepted to ICRA. It's already on arXiv, so you can see it. Is we're trying to do 3D reconstruction for grasping. And so how we're going to do that is we're going to take some partial view point cloud of an object, and we're going to learn to reconstruct it based on having the full 3D mesh in simulation. Okay? But we're not going to learn just to, say, create a new voxel grid or directly learn a mesh. Instead, we're going to learn explicitly a sign distance function. Because the sign distance function, as most of you should know, is a really useful representation for motion planning. Okay. We can extract a mesh from that sign distance function if we want to at some arbitrary resolution, right? So that's the other nice thing is we can get arbitrary resolution meshes because we have this continuous representation of the shape of the object through this implicit sign distance function. So I'm not going to go into a ton of detail on what we did here, but the main thing is once we learn this sign distance function, we can now add it as an explicit constraint to the optimization and say, when you're moving to the pre-shape, or when you're planning the pre-shape, don't plan a pre-shape that will be in contact with the object. Right? We don't want you to slam the palm into it while you're moving. We can also add model-based sign distance functions to the optimization now. So like the table, we just fit a ransack plane and make it a box and say, don't run into this box. This makes the optimization harder, which is why we have this kind of ugly looking cost function, which I think we can simplify, but we haven't gotten it to work yet. So we're now, instead of doing a simple kind of gradient, very simple quasi-Newton method, we're performing a sequential quadratic programming approach to optimize this, which takes longer. But we're also optimizing the full FK of the arm now. So we're not just floating the hand. We're doing the full collision avoidance for the whole arm, just for the final pose, not generating the whole plan yet. But that's, where we'd like to go is, you see the object, one optimization tells you how to move there. And also, with the sign distance function, hopefully we can plan the in-contact phase of the grasp as well. So now I can say, I want a precision grasp, make it such that the distal link of every finger is in contact with the object as part of a constraint now for the optimization. And the learner doesn't have to learn, oh, this needs to be in contact or not be in contact. Okay. Cool. And again, here we're just using the GMM prior, not the conditional one. Okay. So the main thing is this works, and one benefit it gives us is we can now have the robot grasp objects from the backside where it doesn't have the reconstruction and be more confident it's not going to run into the object. Right, so we have some results in the paper where we explicitly try to have it grasp from behind and show that it does pretty much as well as from the canonical view. Okay. So for the sake of time, I'm going to skip that result. So these extensions to grasping inference I've shown you, right? We can improve the diversity and quality of grasp by modeling different grasp types. And here, this is another one where we're looking at, we'd like to incorporate tactile sensing to build these models jointly. We're also looking at here explicitly modeling the uncertainty of the point cloud estimate so that we can plan grasp where we're making contact with the parts of the point cloud we're more or the reconstruction that we're more confident are on the object. Okay. So that's my first time talking about all that grasping stuff. So, okay. So because of the time, I'm going to pretty much skip the trajectory optimization. I'm just going to quickly tell you the setup and then show you a video. So the idea is we want to move an object that we've grasped in a fingertip grasp from some initial configuration to a target configuration. And all we're going to assume is we know this the transformation, kind of the target of the object relative to the grasp we have, which you might think is, it's a little bit weaker than saying we have the full 3D model of the object. But we are going to assume we don't have mass, center of mass, inertia, any dynamic properties of the object. Okay? And we want to move it to this new grasp, and we're going to generate a kinematic motion plan to do this, where we don't make or break contact between the object and the hand. Okay. So the main thing is we can turn this into a big trajectory optimization problem by making some assumptions about the connection between the robot and the hand. You can see the RSS paper or Autonomous Robots papers for the details. But the main thing that's cool is we get this trajectory optimization that can move these objects without dropping them. You know, we compared our method to 3 other approaches. Ours never dropped the object once across 500 trials. So, you know, we don't have any way of predicting whether it will work on a given object, but if you have a good initial grasp and the pose you want to move to is within the workspace of the hand, this works quite well. So, yeah, so here's a bunch of different objects moving, just to prove to you it really does work. We've extended this more recently in a planner to also add finger gating, but it doesn't work on the robot yet, and we have to add some tactile feedback. We can also do motion. If you have a model and you have a model of obstacles, we can also add in a collision avoidance constraint between the object and the environment. So we can, actually I think I have a video of that. Yeah. So we can do things like move this banana around the pear without hitting it, right? Which just comes from the fact that we have this whole thing as a trajectory optimization, so anything you can do in trajectory optimization, easily we can just kind of tack on to this optimization. So now I'm going to very quickly talk about this multi-object pushing paper. So our motivation is if you have a pile of coins, say, on your dresser, and you're going to put them in your pocket in the morning before you go out. I mean, I don't know how many people actually use coins anymore, but this was, 10 years ago when we originally came up with this idea. We still carried coins a lot. You don't need to reason about each one of those coins individually, right? The same holds true of like a stack of papers that you're organizing or many other things that you manipulate as a collection, right? And traditionally in robotic manipulation, we like to know where all the objects are and then plan how we're going to manipulate each of these objects to achieve some task. And so the question we wanted to ask is, can we have a representation that allows us to operate directly at this level of the collection? Okay. And so we've set up this task where we want to put some collection of objects that might have a different number in different trials. So in this case, we have, I think, 10 blocks, but other cases we'll have 5 or 3 or 20. And we want a single representation that will work for all of these. And so we want to move from this green target area to the red one. And these areas will vary between different trials. Okay. We're also learning representation that works with different kinds of objects. So this is, again, a single network to work with different things. So we also show we can push, say, silverware, even though we only trained on blocks. So this is kind of a 2-phase learning process. So in the first phase, we learn a representation of objects. And we do this in simulation. So we take, in our simulator, we know where all the objects are. We know their 2D poses. And so we take a graph neural network, which allows us to deal with a variable number of inputs. And we learn an encoding phi s that predicts the ground truth poses of all those objects as a mixture density network. We additionally learn to directly predict the same thing from an image. Because when we deploy to the robot, we're not going to have access to this ground truth poses of the object, right? We just get an image of the scene. Once we learn this by generating a large number of different scenes of these objects, we can perform a standard off-policy deep reinforcement learning algorithm where we use this learned embedding as the state for learning, right? This phi is now going to be essentially the features of the state that are sent as input to the policy that we're learning. Additionally, we learn this in an actor-critic way, which allows us to use the ground truth embedding phi s to evaluate the critic and the reward function, which gives us a more stable learning function, learning signal for learning the RL. Okay. This is just the neural networks blown up in more detail. I'm going to skip that for time. So here's what the MDN learns, right? The red dots are, the red X's are the ground truth object poses. And then we're visualizing the density, the probability that an object is at any given point in the scene. And here we're comparing to some alternatives. So if we just use a standard multi-layer perceptron, it does a very bad job. If we use the CNN without some special graph neural network structures, it does okay, but not as well as if we add the neural network structures. And on the far right is what the graph neural network itself does, which is even better than the convolutional neural network, right? Okay. And so, long story short, this works. And here's the video on the real Baxter. So the action space for the RL is a discrete set of pushing angles, 8, that we select at different locations relative to any point in the scene. So you give it a 2D position in one of these 8 orientations. So it's a relatively large pushing action space. And we can use slightly different formulations that work okay, but if we try to just learn an autoencoder directly from vision without having this graph neural networks embedding, it essentially just pushes over and over again in the same bad motion. Okay, and there's we have hours of footage of this on our website if you really are bored and don't have anything better to do and want to find where it fails. But so yeah, so here's different configurations, different number of objects. We can use different kinds of objects. So we both tested silverware and just wadded up paper balls, which have huge color overlap between this white tablecloth and the white paper. So it's really learning to essentially do background subtraction of where is stuff in the scene, and then go push where that stuff is. Right? This was, I think, a cool approach to doing it, and we're one of the first people to use graph neural networks. I think we're the first people to use it for manipulation. And so I think this opens a lot of interesting questions of how can we use this. Another thing we're interested in is, can we encode shape information with the same structure? So if we do have 3D information, can we now start saying oh, this object is actually shaped differently than that one, and we don't just care about the position and treat them all the same. Okay. So since I've already gone over, I'm just gonna skip this stuff. I'll tell you a little bit about what we're doing. So we're adding tactile feedback to both grasping and in-hand manipulation. We're also doing joint planning, I said, of manipulation and object learning. We're also doing some work on multimodal, multisensory learning. So here, learning with audio, tactile, force, all this stuff in big, crazy neural networks, and trying to actually interpret what those neural networks are learning, not just treat them as black boxes. And of course, all the mistakes are mine, all the hard work are my students, including the hard work of photoshopping me into this photo they took last summer when I was out of town. It's pretty good. Yeah.